So today we have one of leading pacemaker DKEM, Kevin Non, Vice President of Technology and Marketing at DKEM, is going to talk about reliable metallization solution to accelerate mass production of n-TOPCon solar cells. Kevin?
Okay, let me share my screen.
Yes, please.
Okay, can you see my screen?
Yes, maybe you have to go. Yes.
Okay. Hello, everyone. This is Kevin Nan from DKEM. It's my great honor to have a talk today. My topic is reliable metallization solutions to accelerate the mass production of TOPCon solar cells. Firstly, I would like to have a brief introduction to DKEM. DKEM is actually founded in Wuxi, China in 2010. During past 10 years, DKEM has grown itself to be a global leader in photovoltaic metallization. Right now, we are actually doing two businesses. First one is we are providing high-performance sure pastes for photovoltaic metallization, and we are also providing high-performance electric adhesive for semiconductor packaging. In 2020, DKEM became the first listed Chinese company in sure paste sector. Last year, our sales revenue reached $400 million. As you know, DKEM is the global leading supplier in sure paste for photovoltaic metallization. We actually have the complete product portfolio and technology roadmap to cover different kinds of sales technologies. We have sure paste combinations for P-type solar cells, and also today's folks, we have complete solutions for kinds of P-type solar cell technologies, including TOPCon, IBC, and HJT. And also we have some products to cover module interconnection. And if you look at our activity in TOPCon solar cells, it can go back to 2017, starting with sure paste combinations for unpaired solar cells. We work closely with leading customers like Jinko Solar. Then we upgrade our combinations to the total solutions for TOPCon solar cells, including the DK71A front side finger and the shared DK81A busbar paste. And also we have the DK93T sure paste that for the backside metallization. And we actually committed to keep providing high performance sure paste to help customers to do different kinds of solar cell technologies. Starting from this page, I just want to highlight what's the difference between the TOPCon solar cell and the previous unpaired solar cell. The biggest difference is actually happening at the rear side. At the rear side, we introduced the tungsten oxide layer together with the phosphor-doped polysilicon layer. This is a major difference. With this kind of passivated contacts, it gives us lots of benefits, including the carrier selectivity and excellent passivated quality by polysilicon layer. But to the sure paste supplier, most importantly is that with these passivated contacts, we do not need to metallize the electrode to contact silicon base directly, like BSF or PERC solar cells. With this kind of indirect contact, we can improve the general metal significantly. That means a lot to the metallization and give us a different strategy to do metallization for solar cells. As previous talk shared, right now for the TOPCon solar cells, the mass production efficiency is mainly between 24.5 to 25% in mass production. And with this kind of situation, what can we do to help customers to achieve more than 25% TOPCon solar cell efficiency? Here we study some literature and also based on together with our metallization practice. Here is in the left part has breakdown of the efficiency loss, you can see that the major loss is still happened at the front side, then is the bulk. The second place is the rear side. That means the major opportunities still be on the front side. We also summarize this and try to link with metallization action items. So we summarize into three categories. First is the front side metallization. The biggest issue is still the metal recognition. That's what we need made biggest effort to. That one is we can also try to do some emitter design to reduce the emitter recognition. And also for the contact resistance is always an issue to paste systems. So we have to pay a lot of effort in this part, and always we observe the trend that for the lower and lower laydown that requires lower and lower resistance. This is a challenge. That things we still need to reduce the grid line resistance. Also, for the front side metallization, reduced shielding is always the theme for us. So how to modify paste to enable less than 15 micron finger opening is also an issue and action item for us. The second category is on the rear side. On the rear side, as always, we always talked, we need to do thinner polysilicon layer to reduce absorption from polysilicon layer. Also need pairs to have this. The other one is we need to reduce the passivation recombination. Mainly we use alkaline polishing. This also need pairs to work with it. And for the rear side, we still need pairs to reduce metallization recombination, and also contact is quite important at the rear side. We want to highlight here, for the rear side metallization, we can reduce cost and achieve lower laydown. This is our main effort here. With this kind of request, we have to achieve very good contact resistance, either to enable lower laydown or enable better EL yield. That's very important. Last one is for rear side, we still need to enable fine line printing. Here is less than 18 micron finger opening. The third one, what we want to highlight, is a cool firing process. So for the both front side paste and the rear side paste need to target for lower firing temperature. That's why DKEM developed the total solutions. We have our front side zero paste combinations, and also we have our rear side combinations to work together with the customers. From this page, firstly, I would like to talk about how to achieve a good contact with p-type emitter for TOPCon solar cells. It's quite different from the n-type emitter like the PERC. Comparing to the n-type emitter, to the p-type emitter, its surface concentration is quite much lower than the n-type emitter, and junction depth is much deep than n-type emitter. Generally, the depth is around 0.8 micron to 1.4 micron. For the concentration is mainly around E18 to E19. It's quite different. And the other one is that for the p-type surface is a length of electron, so it's not good for the reduction of silver ions solved in the glass system to form the silver crystallites during silver paste firing. For the silver crystallites, it will play the role of direct conduction. It plays a dominated role for the contact formation. So the issue is how can we promote the formation of direct conduction for p-type emitter? That means a lot to the success of TOPCon solar cells. We mainly have two methods. First one is try to generate a big size silver alumina spikes with incorporation of alumina powders. The second one is try to facilitate more and larger silver crystallites. In this talk, we mainly focus on the first strategy. In this page, we want to talk about how to form the silver alumina spikes to generate a good contact with p-type emitter. With the incorporation of alumina powders, you can see the ASEAN pictures in the middle. it was etching its SEM pictures after cleaning and etching. You can see that there is lots of large size silver aluminum contact spots. That's the direct conductions. So we would like to know how to form this kind of direct contact. The right picture shows the mechanism, how to form the silver aluminum spikes. Actually, with the incorporation of aluminum in silver paste, the melted glass flakes will etch silicon nitride and aluminum oxide stack layer to create local holes for material exchange between the liquid silver aluminum phase and the silicon in emitter. Finally, a big size silver aluminum spikes will form in the emitter, or some of them will even penetrate into silicon base. This kind of big size silver aluminum spikes will take a role of direct conduction channels. Actually, unfortunately, such big size spikes will cause severe metallization recommendations. So it's very important for us paste supplier to reduce recommendation while achieve good contact. This is quite important for the TOPCon front side metallization. So how can we control this kind of spikes to get a balance between the contact and the recombination? The first one, we would like to talk about how to control spikes to achieve good contact. The left part of the SEM is that the baseline paste, you can see that there is less of the imprint. The imprint means the original locations of the silver aluminum spikes. And after we adjust our glass system and also optimize our aluminum selection with DK71A aluminum silver paste, you can see that there's lots of spikes that give us a great benefit on the contact resistivity. But we have to pay attention that too big size of spikes will cause a high general metal, give loss of metallization recombination. As we all know, reducing general metal is a long-term request for TOPCon front-side metallization. But we have realized the other fact is that during the TOPCon mass production practice, customer achieve lower and lower laydown. This also gives us urgent request on the contact request. So we need to balance this very well to achieve the overall good TOPCon solar cell efficiency and performance. This page, we would like to talk about how to control the spikes to improve the recombination. Actually, based on the simulation, we learned two things. First one is the smaller spikes is actually almost have no impact on the general metal, but too big size spikes impact the general metal greatly. That thing is that deeper emitters almost show more tolerance to large spikes. So this gives us three strategies to achieve lower recombination. First, we can design deeper junction or use the selective emitter to weaken the impact of spikes. The second one is we can try to modify our silver aluminum paste system to achieve a smaller spike as well, because it's a thermodynamic process. So we can modify our paste inorganic system, try to control the process. The third one is that we can always use lower thermal flux firing to help control the size of the spikes. With those of the efforts, we can control the size of silver aluminum spikes, then deliver a good recombination. This page is actually based on our metallization practice with different customers. Here we show three kinds of emitter. First two is homogeneous emitter with different surface concentration and junction depth. The third one is the SE type emitter. Actually, we want to highlight the first one is homogeneous emitter with lower surface concentration but a deep junction. Because this kind of design will give us lower contact resistance potential and give a lower risk on spike recombination. And also it's friendly to fine line and low laydown trade. The other thing is quite important is that this kind of deep junction give us robust reliability. For the high surface concentration shallow junctions, most of its performance is opposite, but also it has some benefit on the diffusion time and also have a lower emitter recommendation. And for selective emitter, it's actually the combination of the advantages about two emitters and mitigate their risks. And on the surface, on the metallization area, is high concentration and deep junction. This kind of selective emitter is quite good for long-term technology evolution with robust reliability. That's why it's quite so hot in the industry. This page, we try to show some results. We work with different customers in the industry. First one, we learned that with the deep junction, our paste can indeed show the higher VOC and higher field factor, eventually better efficiency benefit. You can see the data with 1.3 micro deep junction. The efficiency benefit is much better than the shallow junction. The second thing is that with SE type of emitter, our DK71A zero alumina paste right now can deliver more than 0.2% efficiency. With optimization our paste and process, I think 0.3 is possible. And already our paste can work with customer to achieve more than 25% solar cell efficiency in mass production. This is our effort on front side. Rear side is also quite important for TOPCon solar cells. So the next two pages, we will talk something about rear side metallization. The first one is the morphology impact. Right now in industry practice, alkaline polishing is widely applied to TOPCon rear side to further enhance the passivation. But it gives us a lot of bad things is the contact become very poor and the EL issue happen. So what's the reason behind this, and how can we deal with paste? With the polished surface, the melted glass actually tends to cover the whole surface, which actually limits the direct conduction with silver crystallites. This gives us a weakened contact performance that make the phenomenon much reasonable. And for DKEM, we can do a lot of things to modify our paste. We can adjust the flowing and etching properties of our glass systems. With this kind of effort, DK93T silver paste improve the contact performance significantly with a polished surface, even with low laydown conditions. The second thing we want to talk about the rear side metallization is the auto-thin polysilicon layer. The industry practice is actually well aligned with academic results on the polysilicon thickness. The comfort zone of the polysilicon layer is actually between 100 nanometer to 150 nanometer. This quite aligned with between the industry practice and academic results. When we want to do the thinner polysilicon layer, we always observe two things. Actually, it is a headache for metallization because we observe that the gen metal increased and contact resistivity increased at the same time. This gives us a lot of headache. So we studied what's happened, what's the reason behind this. Then we studied and found that with thinner polysilicon layer, the R sheet increased significantly. This is the first one. The other thing is that looks the tungsten oxide layer has a barrier effect for phosphor diffusion. So you can see that for the doping profile for the polysilicon layer, the doping level dropped significantly around the tungsten oxide layer. This mean the barrier effect. Those two makes it difficult to contact with ultra-thin polysilicon layers. So for DKEM, we actually developed our paste and modify it. We made a lot of effort and have about two phases. Phase one, we reduce the contact resistivity easily, but the gen metal is still very high. Then we modified further. We achieved quite low contact resistivity. At the same time, we achieved very low general metal. So that means DK93T surface platform is actually designed to customize with such challenging conditions. So we are actually confident to push less than 100 nanometer polysilicon layer into mass production. In phase one, in the phase one of TOPCon mass production, customer will always want to achieve the good efficiency and the quite good yield with 120 nanometer silicon polysilicon layer. But in the phase two of TOPCon solid cells, I think we have to achieve less than 100 nanometer polysilicon layer. This is the right thing to do. So we get ourselves well prepared to do this. Here we go to the summary page. I think we have already touched most of the points. Here I just want to highlight that the DKEM is very well prepared. We have our integrated metallization solutions to help our customer to achieve more than 25% TOPCon solid cell efficiency. Okay, Shiwang.
Okay, thanks a lot, Kevin, for this very nice full insights into the metallization segment. There are some questions, but we are a little bit behind with our schedule. So why don't we really move into the panel? Anyway, you are part of that, and then we can address some of the questions there.